We do what we do in our everyday lives. We go to school, we work, we cook, we eat and drink, we watch, and we walk. Through the normalcy of our lives, science is unconsciously applied in different events in our lives. We might think that science is done and applied in classrooms and laboratories, but in truth, science works even in doing simple tasks. It may come as a surprise, but yes, science can also be a catalyst in special happenings in people's lives, and we simply cannot distinguish it because we are too oblivious to notice. Heat can travel from one place to another in three ways: conduction, convection, and radiation. Conduction and convection require matter to transfer heat. Conduction is a transfer of heat between substances that are in direct contact with each other. The better the conductor, the more rapidly heat will be transferred. Examples of conductors are metals like coins, spoon and forks, jewelries, wires, and others. Like human beings, heat conduction has different kinds of behavior. Thermal conduction: the conduction of the heat through direct contact. Electrical conduction: the conduction of electrical current, such as through the wires in your house. And lastly, sound conduction, also known as an acoustic conduction. Convection is a transfer of heat by circulating it through air or liquids. Unlike conduction, in which there must be direct or indirect contact between two objects for heat transfer to take place, convection relies on the circulating motion of the molecule in order to transfer heat. An air conditioner works in a similar manner. Hot air from the room flows into the evaporator, and the compressor circulates from the evaporator to a condenser. An example of convection includes heating water on the stove. When heating water on the stove, the pan itself becomes increasingly hotter due to the conduction, because the metal pot is directly in contact with the heating element.
Conduction is a transfer of heat between substances that are in direct contact with each other, and it mainly happens in solids. The heat is conducted from atom to atom using the kinetic energy of the particles, in other words, by vibrating. The better the conductor, the more rapidly heat will transfer. Have you ever noticed that metal benches tend to feel colder than wooden ones? Believe it or not, they're not colder, they only feel colder because they conduct heat away from your bottom better than wood, and you perceive that heat leaving your bum as cold. Metals are particularly good at conducting heat because of their free electrons that move about the structure, colliding with the positive ions and transferring the kinetic energy to them. Convection happens in gases and liquids. As a gas or a liquid is heated, it warms, expands, and rises because it is less dense. When the gas or liquid cools, it becomes denser and falls. As the gas or liquid warms and rises, or cools and falls, it creates a convection current, which is what transfers the heat from one place to another. For example, if you turn on your radiator, despite the name, the room is heated by convection. As the air is heated above the radiator, it expands, rises, and the cooler, denser air sinks, causing a convection current around the room.
Radiation is a method of heat transfer that does not rely upon any contact between heat source and the heated object, as is the case with conduction and convection. No mass is exchanged and no medium is required in the process of radiation.
We might not notice it, but we are greatly influenced by this kind of radiation. For example, we were told as kids not to look directly at the sun, for it would burn our eyes. So we were advised to wear sunglasses to protect our eyes from these harmful rays. Sunblocks with different SPFs were also invented to protect our skin from the harmful UV rays that the sunlight emits. But sunlight is not the only radiation that can transfer heat. The air waves coming from the microwave and the gas stove are also types of radiation that can transfer heat.
Heat can be transferred from place to place by conduction, convection, and radiation. Today, though, we'll be focusing on radiation. All objects emit and absorb infrared radiation. Even we do, just a very low amount, but it can still be picked up by thermal imaging cameras that detect the infrared radiation and convert it to visible light. The hotter an object is, the more radiation it emits. Some of it even becomes visible light that we can see. Infrared radiation is a type of electromagnetic radiation which has a lower frequency than light and involves waves rather than particles. This means that, unlike conduction and convection, radiation can even pass through the vacuum of space. This is why we can still feel the heat from the sun even though it's 150 million kilometers away from the Earth. Some surfaces are better than others at emitting and absorbing infrared radiation. Dark matte surfaces are good at emitting and absorbing infrared radiation, which is why solar panels are black in order to absorb the maximum amount of heat for your hot shower. White, light, shiny surfaces are poor at absorbing and emitting infrared radiation, but they are good reflectors, which is how a thermos works. If you want to keep your cup of tea hot all day, you put it in a thermos that is coated inside with a shiny surface to reflect the radiation back to the tea and keep it warm for hours.
The term thermodynamic comes from two root words, thermo, meaning heat, and dynamic, power. Thus, the laws of thermodynamics are the laws of heat, power. As far as we can tell, these laws are absolute. All things in the observable universe are affected by and obey the laws of thermodynamics. As everyone can see, the balloon's volume, which is known to be the system, is at constant zero. But when external heat is applied on the plastic bottle that is attached to the balloon inflates. What does that prove? If a system's volume is constant, like the balloon, and heat is added, like the hot water, its internal energy increases, or the inflation of the balloon. Contained in the balloon is the unusable energy left. All the usable energy has been used when Ralph played with the balloon. Unusable energy cannot be transformed into mechanical work, hence its name. Notice how the balloon pops and the air molecules move from high temperature or compressed air molecules to low temperature, the air-conditioned room. Absolute zero is a temperature that an object can get arbitrarily close to but never attain. Temperatures as low as 2.0 times 10 to the negative 8th power Kelvin have been achieved in the laboratory, but absolute zero will remain ever elusive. There is simply nowhere to put that last little bit of energy. This is the third law of thermodynamics. It is impossible to lower the temperature of an object to absolute zero in a finite number of steps.
Down, so beautiful, but a line so unusual. Words can't define. Been running through my mind all day. I'm so happy you're mine.